recording session. So chapter 9, the new chapter 9 that I move it, right, is about discrete choice. And we're going to study a particular model of discrete choice. It's called logic, okay? So the idea was basically studying this simpler version of consumer maximization, where instead of choosing bundles, we just choose discrete objects. So examples of discrete objects are, for instance, buying a car when you went to buy a new car or a used car, and then what is the set of alternatives here? These are going to be, for instance, all Honda Civics of different years and different conditions, right? That you see on London that you can purchase, right? This is your choices, okay? So capital J for now is going to be fixed. Right now we're going to fix the choice set and be mindful about that because we're going to move then these choice sets. So we're going to allow experiments where consumers have different choices, right? So remember that in the discrete choice, in the original part of our choice investigation, we study this situation where we have variation in menus, variation in alternatives, right? We have an experiment where we are giving the consumer different menus and they can choose from it. Right now, we're going to fix such a menu and then we're going to change prices, okay? And then the problem of the consumer is going to be maximize utility. And this utility is indexed by the individual, of course. So each individual has their own utility. And now I have also this price that is indexed by J. What is J is the index of the good. One of the items in the choices, for instance, one Honda Civic of make 2000, right? And then I have this outside option, which is the remaining money that you will have. That is basically the difference between the income of each individual and what you pay for the alternative. Since this is just a discrete option, it's not multiplied by quantity, but it's just the price of the alternative J. So we're going to maximize this object, and this basically requires you to choose one alternative. In particular, we're going to have a particular alternative, which is J0, which is non-purchase. So I don't buy any Honda Civic. I just I would like to bike or walk or whatever that is different from buying a car. And then this is going to be the outside option, right? In that case, you use all your money on the outside option. So basically, that's you save all what you will have spent on the car. So now this problem is simpler than the consumer maximization problem. So you don't need here to do differentiation or further conditions, right? At this stage, you just have to maximize. So imagine that you chose J, fix this Honda make 2000, and then compute the indirect utility, okay? So what is the indirect utility? So imagine it costs a certain price PJ, and now the remaining, basically what you spend or the savings that you have is Y minus PJ over PZ, okay? Now we replace this back inside this utility, and so Z is replaced by this quantity here, Y minus PJ over PZ. Now, yes?
So I would like to know, here we assume that the consumer only buy one brand.
Yes.
Okay.
So you in the commodity chapter 3, right? So you could buy quantities of many goods, right? Here you instead have exclusive goods. So if you buy a Honda, you were gonna buy one, right? And that's it, right? You cannot buy the Honda, a Hyundai or a Ford, right? So you just buy one car. So this is discrete choice, that's the different part. And so here we're going to replace set by this quantity. And now we have the indirect utility, okay? So this indirect utility is going to be basically given by these changes in, there's a missing J here. So this is just replaced back by these quantities, and we obtain this value that depends on X, which is a vector of characteristics, mileage, how good, what condition the car is in, and so on. And now we have also the utility of the outside good, which is just not buying a car. And in particular now, how do we maximize this utility? Well, instead of looking at the problem with a budget, I just can go and check the indirect utilities. So I have in my mind what will be my benefit of buying a Honda versus a Ford versus a Civic. And then I just choose the object, J, that is the one that gives me the highest utility, including here, not buying a car. So that's, is everyone on the same page, right? So this one here is telling me this will be the behavior of a consumer, and basically it's telling you, you will buy one alternative out of the capital J, including the alternative 0, which is not buying a car, okay? So in these cases, I'm just maximizing the highest indirect utility I will get. So I'm maximizing, again, utility. I'm just choosing the good that gives me the max utility. So now, so what happens at the level of one? Yeah, questions?
Yeah. The z equals to y minus the relative prices, or just the difference between y and pj, then divided by price z.
Sorry, so we go here, right? And then there's a missing y here. So we have,
Maybe
yeah, yeah,
first
yeah.
you.
Yeah, I
Yeah,
get
yeah.
it completely. Sorry. So usually in this, I use this bad notation from all times, right? Because I'm older than you. That is this inline division, which is supposed to say everything before that is divided by that. Yeah, but so you have y minus pz divided by pj, right?
Yeah.
Yeah. Okay. So that's simple, of course. And now we got you replace it back, and now you get this object here, which doesn't depend on the set. So you just have now a problem of choosing the max j. So including the outside option. Okay. And the outside option is given by this utility, which is we usually normalize it. We usually make it equal to 0, right? So here I'm going to put a parenthesis. We normalize in the sense that it's just a degree of freedom we have the model for all individuals, right? Now, with this in hand, what I'm going to do is I'm going to think of the decision problem. So I maximize the J, and what is the result of this maximization, right? Is basically a discrete choice. So individual I will choose J, right? Whenever Uij star of all these things here is greater than equal. In this case, let's do a strict for all the Uj's prime for all J different than J. Okay? So this is just a binary choice. You choose J whenever this happens, else you don't. Okay? So this will produce, so if you see a data point, a data observation from an individual, then you will see ones or zeros, right? So you see Civic, Honda, Hyundai, whatever, Ford, whatever, and then you see a 1 in each particular column corresponding to whether this was purchased or not, okay? That's it. This is mutually exclusive, so only one of them can be chosen. So no bundles here. And okay, so then how do I model this problem? And also, how do I think about this problem? So here there are two things I can think about. So in particular, trying to predict discrete choice is usually is super difficult, because how many times do people buy cars? Like in particular, possibly if you get a car at all, you're gonna buy possibly one that lasts during your PhD, right? I did that at some point in my PhD in the US. So in the US, it's very hard to not have a car. Now, so what do you do with that? I only did it once, right? So how people are gonna model what I do? If just one time I did it, right? So in order to have some sort of understanding of behavior, I need repeated choice. Do you understand? So that's a big difficulty in discrete choice, right? So in general, I don't have like many repeated choices of individuals in some particular markets, like card buying. In other markets, for instance, you have a lot of data, right? Like for instance, right now, you know that in Spotify, sometimes you choose out of menus of playlists, you choose one of them, right? Or Netflix. So that's repeated choice from an individual, right? So sometimes you have a lot of discrete choice from an individual. Now, the second issue, which is more fundamental, even if you have data, is that when you have discrete choice, then we're actually facing a very big issue, right? Because this prediction tells me that you will choose the utility that is the maximum, right? Now, imagine you have some small variation in this utility, so some small stability change. So you have a shock on your preference. Now, for instance, a mood, a craving for some different alternative. Like this obviously can happen in choosing on movies on Netflix, right? So one day you're not in the mood for watching comedy movies. You want to watch a thriller or a horror movie because it's October, right? And that's a shock, right? So now these small changes will change the prediction very easily because in the end, it's just about this inequality. So you shock that, and then you're going to change the prediction. So you're going to have a lot of instability in these choices, right? Because there are ones and zeros. So small shocks to your preferences are going to switch you around. So then obviously trying to understand these ones and zeros is kind of nonsensical, right? So you're going to have them flying around in repeated choice. Now, now what I just described is what is called individual stochastic choice dataset, which is something very difficult to handle. So we're not going to deal with that in this class, but I want you to know this exists, which is basically repeated choice from an individual in some problem that is more or less static, right? For instance, if you're watching shows on Netflix, imagine you are thinking kind of broad categories of what this the individual likes, like comedy movies versus thriller movies versus no sorry, Oscar winning movies, whatever. So these are the categories, right? So if you choose every weekend that you like to watch movies, then you're gonna get a new draw of your choice, right? So we're gonna get a new observation. Then if you do it for many every weekend and you have a year, we're gonna have the frequency of choice of each type of movie. So that's individual stochastic choice. There are a lot of issues with that particular kind of data because there are issues such as dynamics, right? People may change what they like, they may learn what they like, and they may get bored and whatever. So that data is very hard to model. So I'm not going to talk about this data in this particular class. So I'm going to talk about a different kind of data set, which still has to do with a stochastic choice, which is the interpretation of a cross sections of ones and zeros. Okay, so let's go back to the markets of cars. And now, again, so I'm a used car dealership, right? And I want to know which brands should I purchase more often from the people that offer to sell to me, right? So which brand do you think you should focus on, right? If you want to maximize profits, right? You may also, in general, if you are trying to put you're trying to understand some service about repairing cars that are old or buying parts. You have a store. You may also want to know what is the frequency of choice of different brands in the car industry. So what do? You, instead of thinking of individual stochastic choice, you think of what is called a cross section of ones and zeros, which is market shares. Okay, so this is the aggregate behavior. Okay, so what I'm going to tell you now is that the way to think about this is that you take pretty much all individuals in London, that we have a sample of individuals in London, and then we check whether they have purchased a car, right? It's always possible to not purchase a car. And then you have the probability of purchasing the different brands, right? And then we add them up, and then we have the fraction of people or the share of the market that goes to Honda, to Hyundai, and to Ford, okay? And to the outside option. So do you understand? So this is just the fraction of people buying different brands for a fixed market. So now we're going to fix a market. This is very hard to do in reality, but for this example, we want to define, London, Middlesex area, right? This is going to be our physical market, and then we can compute shares there. Okay. Now,
excuse me, Professor, I have a
Yeah.
quick question. So in this epsilon term, this random shock, could we also see this as a random shock in one's income, for example? Like if somebody loses their job or
so income is harder. So in particular, you can see from this framework here, right, that this structure tells you that you have this additional variable, right, that kind of absorbs all income effects. So in a way, so basically, the only part that is going to depend on the income is really the outside option. So this is a very particular class of models that simplifies our analysis a lot. And they are called basically quasi-linear models, right? So in that sense, income is not going to play a role right now. In fact, the way people assume are able to deal with these models initially, right? Then we can make them more complicated, is by assuming preferences shocks are independent from income. Now, that's of course not real. And that's going to create some issues with endogeneity, right? So that's for the estimation part. But right now we want just a benchmark model. So you can actually think of all this analysis conditional on income, right? So imagine that, you know, we're just thinking of a slice of the population that has same income, okay? Or comparable income, okay? So income is something I don't want to deal with now. So let's think of this analysis as conditional on income, okay?
okay, thank you.
Okay, so so how can I model this in a way that is reasonable, right? And this is what is called discrete choice model. So instead of having this completely random utility, which can be anything, right? I now imagine that there is an average utility that only changes among brands and depends, of course, on the characteristics, observable characteristics of these brands, the price of the brand, the price of the outside option, the income of the individual in this sense for the outside option, right? And now we have this, and we can fix it now, as I mentioned. And now we have these epsilons that are shocks to each individual and to each brand, okay, or each alternative. And these can be interpreted in many ways. The main interpretation, for instance, may be that these are unobservable attributes, right? So things about the cars that I don't see as the econometrician, as the modeler. There can also be preference shocks. So for instance, these are moods, things that you like. And then preference heterogeneity, right? So that just means that different individuals are just different in some way that I don't understand. And I'm going to think about this in this additive sense, okay? Okay, so before continuing, right? As I mentioned, this normalization of the utility of the zero, right? When we're talking about this random utility model, is that it's going to be zero only for the mean utility. And this mean utility is going to be for the outside option zero. So that doesn't mean it has no utility to not buy a car. It might be that some alternatives or cars that you buy will give you a negative utility, right? So it's just a reference point. So the only thing that matters here are differences in utilities. So for now, let's think about the individual stochastic choice data set. And in particular, imagine I do have this ideal experiment, which is very hard to obtain in real life, which allows me to repeat the same choices for an individual, you know, thousands of times. So this is kind of the Netflix data, right? So here, what I want to obtain is the probability of choosing alternative J for individual I. Okay, so this is individual stochastic choice data. And here, what I will do is basically take the probability that these shocks here, epsilon j and so on, are such that this difference is always positive for all j different from j. So what does it mean? So I can also rewrite it in the following way. So remember that basically I can rewrite this thing as the differences in the indirect utility, right? And here you have this epsilon ij minus epsilon ij prime, okay? So what you have here now is that this is a random utility term. this is a difference of this random is also a random variable. And now you have here a deterministic quantity, right? So now in this particular case, now you can start thinking of the CDF of this difference on epsilons. So everyone understands what's going on here. So this will be for a single individual, right? And then now imagine, for instance, that in order to make a population interpretation, I can also assume that these epsilons are IID across individuals, right? And then I can compute basically the market share from an alternative J, right? For this, basically, we're going to obviate now attributes just for prices and basically the vector of income, right? And this is going to be, again, given that we have IID distributions, is going to be, again, this object here, okay? And then these are random variables. They are no longer indexed by I, right? Because all of them are identically distributed. So we're just going to write this thing. Yeah, so we can just obviate the I here. Okay? So in this particular case, we have now a share. Okay, it still works like a probability, adds up to 1, is weakly positive, and it's just this integral. Okay, so these are the two interpretations. So market share is the cross section of discrete choice, and the other is individual stochastic choice data. So what I'm telling you right now is a lot of information, but basically there are two things I'm telling you that are notable. The first thing is that even if I have only choices from one individual, your choices may still be stochastic, okay? So what I'm telling you is a big deal, right? So I'm telling you all this maximization of utility from before, it doesn't really make sense because your preferences are never stable, okay? So for instance, if you have a stochastic choice, you're not going to satisfy warp, okay? Because you're gonna be flipping around different choices, okay? So this happens obviously in different choice situations, like choosing a movie, choosing food, and so on. You're going to be flipping among alternatives. Why you do it is just because you get shocks to your preferences, right? So this is about really the predictability of individuals. So we stop being deterministic, and now we become stochastic now, okay? So now I'm allowing each individual to have a random choice. So now, what does it mean in terms of predictability? So it means that if I want to, let's say I see two choices, for instance, from a single individual. Can I do something about trying to predict what they do? So remember that I told you that with warp, with a weak axiom, two choices from menus were enough to test warp, right? Do you remember that? So if I tell you that two choices are enough to test warp, it also means that I can also predict out of sample with at least two choices, right? So you have really small data requirements. Now with a stochastic choice, and I tell you, if you are a stochastic utility maximizer, and now I observe only two choices from you, then what can I do with that? Does anyone have an answer? In terms of prediction, in terms of testing, can I test random utility with two trials?
I would say it really doesn't tell that much information. Your prediction would be not very right, I would say.
Well, it would be really bad, right? And also, one thing so yeah, correct, Yonki. So the key thing is that here, the theoretical object that I'm trying to understand is a probability, right? A probability is basically an abstraction, right? So in the limit, the relative frequency will converge as trials goes to infinity to the true probability. Do you understand? So this is the, you know, what is the difference between an empirical frequency? So the times of successful events over total cases, right? The relative frequencies of times you pick in a finite experiment. This is just a relative frequency. It's not still the true probability. There is sampling variation. So these are not the same objects, right? So usually what you observe in data from final samples are the relative frequencies of choice, okay? So these are usually called hat P, Pij, for instance, and then we're going to obviate this part, and these are going to be the summation basically from the experiment. These are the number of experiments divided by the total number of experiments of what? Of the instances in which pretty much the agent chose J, right? Out of this menu, right? Out of alternatives. Okay, so this is basically what I'm doing, right? For a fixed choice set, I'm counting the times this particular individual choose the alternative J out of the menu. And then I count the times, right? And I divide it by the total number of trials. So this object, right, will converge under some conditions, of course, will converge. This is, of course, a function of K. So we know it also depends on K, right? Usually you don't write this dependence. But as it goes to infinity, under some conditions, it will converge to the improbability, right? To this object. So this means basically that I don't have access to the true distribution. And in particular, you know, this means that in finite experiments, I cannot test this without having to count statistical sampling variability. So I cannot do any more these deterministic tests of it passes or it's rejected 1, 0, but I have to do some statistical tests with a null hypothesis, and then I'm going to have some threshold rule to be able to pass it or not, right? So everyone understands what I'm saying? So this is the issue here, of course, with individual stochastic choice. I need a lot of choices from a single individual, which usually never happens. Still, there are some data sets that are like that, like for instance the Netflix or Spotify data. Now, so what is easier to do is to think of cross sections, right? So the shares. So this is the estimated share from J, right? This is going to be instead just a sample, an average sample, right? So imagine I have n individuals, right? And now this is the sum from individual I to n in a sample of these choices, okay? So of course, this was here for the trial K. Now this is here just for the individual I, okay? So here I is fixed, here I is moving. Okay, so these are two objects that are computed in the same way, but they come from different data. Okay, here we have trials from the same individual, right? And they converge to the true stochastic choice rule in the limit as the number of experiments becomes infinite, right? And shares instead are computed as the sample average, okay? And then you know this sample average will converge to this true share as n goes to infinity, okay? So everyone understands the two kind of data sets we're looking after. So these are cross-sectional objects, and then the others are these time series objects. Now, I'm going to focus more on the shares, but I'm going to now, I'm not going to do a statistical testing. So I'm going to assume that I already have this object here, and then I'm going to do my analysis there, okay? And I do it because it's practical. And I can always do a test for these things, right? So everyone understands?
Hello, Professor. So
Yep.
for the share method, so do you require the sample to be fairly homogeneous?
No, so that's exactly what we want to do, right? So remember that each individual can choose whatever they want, and that's why we have shares with positive quantities for different goods, right? And that this heterogeneity in what they like is going to be modeled with this additive random utility right now, right? Which is you have an average thing that you like about cars having less mileage, you know, being in a better condition, and then you have a shock, and this shock is individual, right? So heterogeneity here is the name of the game. Now, what I want you to notice is that this thing here is, of course, an aggregation problem. So I start with individuals choosing, at the granular level, which was our object of interest before. And now I'm taking an average across the behavior, okay? I'm not taking the average choice, but this is the relative frequency, right? These are two different objects. And I want you to understand the difference. So the average choice here, when you are dealing with cars, is not even well defined, right? But if you have, for instance, a commodities, like the chapter 3, you can talk about the average commodity, right? Which is the aggregate demand. So usually aggregate demand, and this is chapter 4 in Mascola, that I'm going to send you to read, it's very short, is that aggregate demand may not behave like rational. So that means its Zlowski matrix is not rational, it doesn't satisfy GARP, even if all individuals behind it are rational, okay? So the average choice doesn't preserve anything about rationality, okay? Stochastic choice, on the other hand, preserves a lot of structure. And in this case, we have individuals, each of them with their own utilities. And then we observe the outcome of such utility maximization, which are ones and zeros. I take the average of them, which is this share. And then it turns out that the share is going to have a lot of properties that come from utility maximization that is called random utility, right? And this is what we're going to understand today, okay? So now, as usual, it's better to understand these models with a parametric example. So I'm going to give you what is kind of the analogous of the Cobb-Douglas, right, for the deterministic case. And this is called the multinomial logit. So how can I be parametric in this world? Well, what is the main parameter here? Is this random shocks, okay? So these random shocks are the key driving force of choice, because these numbers here are average choice, right? So they are numbers that are fixed across brands. So now all the real action is happening on the shocks. So now I'm going to do the following assumption. So I'm going to assume that each epsilon ij is independently and identically distributed according to what is called the stream type 1 value distribution, which has this CDF, okay? So if you notice, this is kind of a double exponential thing, right? And this CDF is basically the probability of epsilon being less than or equal than this fixed value x. And for this Euler constant, this is a traditional problem. If I go and integrate this problem here, okay? So let's write this down so you understand what's going on. So this pretty much is the integral, right? Over the, I'm going to define the following vector. This is going to be the differences of all j's, right? For all I different than j, right? And now, so this is going to be the, I'm going to call it now. The distribution of this is going to be called delta E, I guess. Okay, so this is a vector. And now let me call it other stuff. Okay. So here, what I'm going to do is I'm going to define this one, which is the binary function that gives you one when the statement inside the parentheses is true. And this is basically telling me that Bij, right, minus Bij prime is strictly greater than the difference in these objects. So this is a continuous distribution. So ties don't happen with zero probability, right? So I can replace this by the weak inequality. And this happens for all j different from j prime, okay? So what we have here is basically this integral that has to be, of course, integrated with respect to this variable eta, because this statement here is happening for all j's, right? So it's a multiplication of indicator functions. So this depends basically on this difference indicator, and this has some distribution. So I'm going to call this the induced distribution by eta. And then, yeah, basically you can have this object here, and you write like this. And here basically you have the eta in its domain, right? So this is going to be integrated in the domain of eta. So in the support of this random variable eta. Okay, so so let me change this. So this is random, and the other is just the value. Okay. Okay. So this is basically telling me that I'm trying to see what is the integration of according to this distribution f epsilon. Now the difference of this type 1 extreme value are going to be distributed with f eta, and now this is a vector, it's a joint distribution over them. I take this integral over that, and now I get this object here. Okay. So this is a problem for calculus 3, and then you obtain this thing that depends only on the individual mean values. Okay. So what is the interpretation of this model? So you have a mean utility, and now this is telling you that the probability is proportional to the mean utility. Okay, according to this exponential factor. So you are making mistakes, but still, if you like, for instance, a little bit more in terms of average utility, alternative Honda over Hyundai, the proportion of time, you're going to be proportional to how much you like this in average. So you're going to choose a little bit more often Honda over the others, right? So that means that the shares of Honda in this cross-sectional interpretation are going to be bigger. Okay. Any question here? Okay. So
yeah, one question, Victor. What's the distribution that we were using, the Gumbel distribution?
Yeah, so this one is called many ways, but one, the Gumbel is one name. This other is the type 1 extreme value. Okay. In general, this model is called the logit model, right?
Yes.
Yeah. So yeah, the Gumbel is also another name. Any other question? Okay, so now we have the independence of irrelevant alternatives. So, okay, we have our first model. And the first question I'm going to ask you is, why do we do this? So in particular, we have a very general model here, right? We have these epsilons can be anything. And now suddenly these epsilon are this type 1 extreme value distribution. And now I end up with this model, which is proportional to the average utility. So does this model, do you think this model is better? What do you think are the benefits and you know, and cons of this with respect to the general formulation? So any input here?
Maybe now that you assume like the shape of these epsilons, like you don't have to guess what they will be in this new model, kind of, maybe.
Okay, so what Eduardo said is the practical question, right? So, okay, these epsilons, they can be, you know, shocks that are undetermined, so they can have any distribution in principle. So now how do I make it operational, right? So how can I actually obtain some particular predictions without knowing that distribution? So that's a fair question, right? So we're going to think more about that and whether we can do something that is non-parametric. But right now, you know, obviously, the same as with utilities, what was the first reaction of theories and practitioners? Is trying to write down parametric models of utilities such that we can do something with them, right? We can do models. So, and why people usually choose the first models, in econ at least, because there was no data historically, right? Is that we usually choose things that are computationally feasible. So what would be the best world if you have this ugly integral here? That this ugly integral has a closed form solution, right? So in other words, I don't have to do it in a computer every time, but I just have a formula. So it turns out that for the extreme one distribution, you have this model here. Okay. So this is one of the few distributions that gives you a closed form solution. Okay. So you can actually write a formula. And this formula actually has a nice interpretation that tells you the probability of choosing J, the brand J, is proportional to the average utility, how much you like something on the average. So that's pretty cool. Now, is there any basis for this? So it turns out that psychologists were kind of ahead of econ by a lot. So in the 60s, we have Luce, right? So this is a mathematical psychologist that was running experiments on repeated stochastic choice for individuals, so individual stochastic choice. And basically what he found out is that if he gave the individual a stimulus, right, so which is some small reward, the intensity of the light of some alternative on the screen, then people end up choosing those alternatives basically in proportion to the intensity of the average stimulus, right? So this is a model actually that came from individual stochastic choice data. Now, McFadden, which by the way won the Nobel Prize for this, he said, look, in econ, we don't have individual stochastic choice data, at least in the 70s where he was working on, right? So we just have cross sections. So we have shares. So is there a way to understand this from the point of view of individual stochastic choice, individual aggregation of many individuals? And then he came up with this random utility framework that I'm telling you, right? So Lu's model was directly this model that you see here, okay? So he just derived it from the experiment. So Luz gave it a kind of micro foundation. So he said, actually, this is the integral of this individual discrete choice maximization when the distribution of shocks happens to be a stream one type distribution, okay? So McFadden gave us the interpretation of the cross section, okay? So McFadden was the guy that was doing the psychohistory thing, right? So he was thinking that maybe we shouldn't predict the individual, but we should try to predict the cross section, okay? So the aggregate behavior, not in the average, but in the relative frequencies, okay? That's very important. So one of the main failures of econ as a science has been to focus too much on average behavior, okay? So if you see, for instance, national consumption, right? So total consumption of anything, that's an average behavior, right? Multiplied by the number of people. So if you focus on that, then nothing about rationality is preserved. So you lose everything. And therefore, representative agents that people use in macro are trash. Sorry to say that, but basically they don't work. So you can have a collection of individuals that are rational and you aggregate them in the sense that I obtain the average behavior, right? And then there is no rational behavior anymore. Rationality is destroyed by averages. However, relative frequencies have a lot of structure, right? And that's the insight by McFadden. So if you look instead at the histogram of choices, that still has a lot of structure. You can do a lot of stuff with that, right? And that's even more realistic because that allows people to have shocks to preferences, okay? So this is the best world. I think this is the correct world of behavior, where you're not deterministic anymore, right? So this is analogous to, basically going from the Newtonian physics, to having now, going to this lack of predictability of individuals, right? So now we have quantic physics. So basically, we can no longer say that for sure an individual is going to pick something. We know it's described by a distribution, right? And only when you're faced with a choice, then it collapses to a particular 1 or 0, right? It's exactly a particle, right? So you don't know where is it until you measure it. So you give here a choice at a menu, and these guys are going to pick something from it, right? But it doesn't mean that their utility is fixed. It's random, right? It's just that it gets realized at a particular choice, okay? So this is the correct world. This is the correct way to do this, right? So what I want you to understand, that's why I skipped chapter 4 from Ascolel, but you have to read it because it's very simple, is that chapter 4 is basically a capitulation chapter. So you say, all that you learn when you try to do representative agents and try to understand aggregate behavior in the sense of averages, is not good. Okay, that's the conclusion of that chapter, right? Here, instead, we're going to tell you we can do a lot of things when you're studying the relative frequencies instead of the average. Okay, so, and the first object, again, this is the insight by McFadden, is trying to understand this first model, which is very parametric, and it's telling you now that I can describe a cross-section of individuals by means of these mean utilities. Okay, and now I'm going to tell you that pretty much the share of people choosing brand J of Honda is going to be predicted by the mean utility of Honda. Okay, so somehow you can predict now how much people like Honda in average. Okay, so I can do models about it. Discrete choice. Okay, everyone understands that? So I'm going to tell you now.
Victor, quick question. Like in econometrics models, sometimes I see that people do not run logit model, and instead they just do some kind of like an OLS. So it sometimes produce negative probabilities, which is not good. But I mean, so
Yeah.
linear models don't have this much complication. I just wanted to know that whether this could work in this context.
It's a really good question, right? So what is the advantage of doing a linear model? So we're going to understand a little bit that in a second, but a quick answer for you is that, so OLS won't assume a distribution on the epsilons, right? So that means that you are actually being completely unrestricted in terms of the type of shocks you're allowing. Of course, you are still forcing the mean utility to be linear, which might not be. Do you understand? And also, you are not predicting exactly to be 0, 1. So I agree that actually OLS may actually not be a terrible model in terms of trying to be unspecified in terms of the shocks, right? The OLS point is that you don't need to specify the distribution of the shocks. Do you understand? So that's the main benefit, okay? Now, why is an issue? But let's understand, and this is a good entry point for this IIA. So the reason why people do it in this discussion between linear probability and logit, it has to do only a bit with behavior. It's more about like to get you know, estimates that are not biased and trying to deal with endogeneity and so on. So these are problems from the econometrician, right? So we are separating the first year, so I'm going to let that to Nail. But for me, what I want you to understand is the implications of the logit assumption in terms of behavior. So what does it imply about behavior that is somehow fishy, right? That we don't like. So we have to understand the implications of this model. So, and these testable implications of these models are basically what is called the independence of irrelevant alternatives. So logit is too good to be true because it's so nice, right? It just depends on the mean utility. It's amazing, right? It's an amazing model. If humans behave like that, it would be amazing, right? But usually it's not the case, and it's not the case because of the following issue. So turns out that if now, instead of having just shares on London, but I also get shares, for instance, on St. Thomas, okay? So St. Thomas is a smaller market, so it definitely has less alternatives for used cars than London. Do you agree? So now, in particular, let's imagine J prime has less alternatives. So in St. Thomas, you cannot buy Hyundai. You can only buy Honda and Ford, and in London, you can buy Honda, Ford, and Hyundai. Do you agree? Now, if I study the relative ratio of shares between Honda and Ford in St. Thomas and London, then logit will predict that this relative share remains the same, okay? And this is the empirical implication of logit, and you can see why. Because if I take and divide the predicted probability J over K, you get just the division of these mean utilities, okay? So in other words, once you divide these probabilities, the denominator doesn't matter anymore. And in fact, the denominator is the only thing that is giving you the dependence on the menu, right? So in particular, this is just telling you that only the mean utility matters in terms of these odds ratios. So the ratios of probability just gives you this mean utility. Got it?
Yeah, thank you.
Yeah, so this AIA is, of course, in particular is something that may be bad, right? This is like the independence assumption. So again, when you have a testable implication of a model, then the first question would be now modernly is whether people in reality behave according to IIA or not, right? That should be the first question. However, historically, because we didn't have the data in econ, the critique came from a theorist and with another mental or thought experiment, right? That was by De Breu, the red bus, blue bus problem, okay? Which originally was way more elitist and it was actually about classical music, okay? And then they changed it in the books to buses to make it, you know, more appealing for the masses. So, you know, academics, especially De Breu, which was in Stanford, or UCLA, Berkeley, I forgot. He, you know, obviously was an elitist guy. And so he, you know, he has this very elitist example. So now, you know, his example was about trying to see substitution patterns and how, according to him, something that looks like a duplicate was going to create very weird substitution patterns. So again, this example is not example coming from real life, but it's something that will make you think whether this model is good. So it's just a thought experiment, okay? So take it with a grain of salt, but this is the experiment, it's famous. So say you have two options, so W for walking, and then you have this problem of red, basically taking a red bus, okay? And then we assume that when you have only two options, you're going to have 50-50. So half of the individuals walk, half take the red bus. So what is the ratio of probabilities? It's 1. Now, the City Transportation Corporation, right? This is the London City Council, and introduces a blue bus, which is identical to the red bus in all attributes except for color, okay? And in fact, it's a nearly perfect substitute, while not being a substitute for walking, obviously. So what should you expect? And this is the key, right? When you say, what should you expect? Is this kind of normative approach to decision making? So this is in the mind of De Breu, right? So he thinks this is unreasonable. So obviously for him, imagine that in this new choice set with j equal to 3, now we have probabilities, and this is in his mind, right? So these are coming from his mind. You have now probability of walking is still half, so 0.5. And then the probability of red bus versus blue bus, given that there are nearly perfect substitutes, are 1/4, 25%. Okay, so now let's go back to the W on red bus and take the ratio. So now it's 0.5 divided by 0.25, which is, you know, 1/2 divided by 1/4 is 2. Okay, everyone agrees? So now, voila, you have a violation of IIA. So this goes against what De Breu thought was reasonable. And therefore, people said IIA is bad. Okay, that was how decision theory was done before, right? Back in the day. But okay, in reality, he has a point, right? So you introduce something that is super close, it's a duplicate, in fact. Let's make it simple, right? It's complete duplicate, but now you study the substitution patterns, which are these ratios. And now suddenly walking over red bus is 2/1, okay? And before was 1/1, so 1. So basically now, so in this model, you should expect that the substitute will just absorb share from the perfect substitute, from the blue bus, not and leave walking alone. But the IIA requires more than that. The IIA requires us to give some of the fraction from the walking, right? Instead, you will have the prediction here be equal to still 1. So so what will be, for instance, the allowed distribution according to logic? It will be that probability of walking divided by probability of red bus is still equal to 1. So these two probabilities should be the same under the new model, right? So if you are compatible with IIA, then in fact, these two things should be the same, okay? So this is incompatible with logic. Now, again, so do people fail logic in real life? Yes. So people have tested, and usually it's not the best model. Now, news for you. Logic is one of the most used models in the world. So a lot of people, the first thing they learn is do logic, right? This is part of discrete choice. Why do they do it? Because it's tractable. The same idea as expected utility, right? People use tractable models not because they are correct, but because they are computationally feasible, okay? And that made a lot of sense in a world where we didn't have good computers. Do you agree? But now we have Julia, we have clusters. I have a computer that has a GPU that has thousands of processors inside, right? Usually people use it for gaming. I'm not allowed to play with it. I just can run models with it, but it's amazing. You know, I can run models in a second. So things that it took in the 90s to run several months, these models of discrete choice, and several arrays from Yale. Now I can do it myself in an afternoon in 10 minutes, right? So, so you need one labor and one computer that costs a lot of money. And but this money is not the same money that Yale spent in the 90s, which was, you know, possibly 100-fold. So we have good computers now. So why do we do logic? Well, we are not going to do logic anymore, and we're not going to do linear models anymore, right? So this is kind of old tech, and of course, all people are doing that, but you're grad students that you have to learn the new stuff. So let's learn the cutting edge stuff, right? And then you're going to learn with Salvador to compute it. And hopefully, if I have a second year class, I will teach you. But you know, the problem about these models is that people start using them because of computational constraints. So I want you to understand this. You know, when you learn anything, you have to understand also the context, the historical context, and the technological constraints, right? So people use these models not because they are correct. And why people still use it is just because they are tractable and computationally non-demanding. But as technology changes, right, we're going to change what models we use, okay? And also as data changes. So right now we have much larger data sets. We can get better shares. Even now we have, thanks to Netflix and Spotify and Uber, we have now real discrete choice data, okay? So individual stochastic choice data. So as a small story, so when I was in the market looking for a job and eventually ended up in Western, I was interviewed by Uber, right? To become part of the demand analysis division. And basically they send you kind of a problem set, right? To get a job. And that problem set involved trying to predict basically a model and discrete choice, the probability of taking a ride, right? Given a set of characteristics. So what was the expected time of waiting? What was your location? What was the price of the ride? And so on, right? And they actually get individual stochastic choice data, right? Back in the day where we use Uber, you know, before the pandemic, then people were doing this every day, many times, right? And in a month, you have amazing data, right? For individual stochastic choice. Okay, so this is basically the new world where we have this kind of data available. So logic, of course, is going to be very lame. So we have to learn kind of the general model. So, but we have to understand logic because it's like the Cobb-Douglas. So this is going to be our baseline. So let's understand it. And now let's gonna be formal. I'm going to be formal about this. I'm going to describe this, take the theorem, and take a break. Okay. So let's start with now formalities. So X is the finite choice set. And then I'm going to define the collection of menus for basically as 2 to the power set minus the empty set. And now take any particular menu inside it, and I'm going to define a stochastic choice rule. I'm going to change slightly the notation here just to make clear that this is this ideal object that we use with choice set variation. So now notice that I'm going to move to a world where I don't have prices, I don't have attributes, it's much more simple. Here, I just have choice set variation. So I go back to an experimental setup where I allow to have choice set variation. So we go back to the environment of the first chapters, right? Where we allowed menu variation, okay? So that means I'm going to have an experiment and I'm going to give this cross-section of subjects different menus, and I'm going to see the share of people choosing from these menus. And so that means basically that I have this probability rho sub A, which is the simplex of these choices. So this describes basically the probability of any alternative that is greater than or equal than 0 for all A in the menu A. And then they have to add up to 1. Okay, that's the stochastic choice rule. And now I have a stochastic choice data set, which is basically the collection of these rules, the row sub A for all menus. Okay, do you understand? So this is the analogous to the choice correspondences that we studied before. Okay, so back in the chapters for deterministic choice, we ended up describing that rationality implied the weak axiom, right, and the strong axiom. Here, instead, we're going to describe what happens with this stochastic choice data set when we have variation in choices and when we have a particular model, the logit model. Okay. So again, why do I do this and why I'm eliminating prices and attributes and so on? It's just because I'm not going to need prices or the rest because they are redundant information once I have variation in alternatives. Okay. So the alternatives that you're facing may be actually determined by prices and income, of course, but they may also be determined by other factors. So this is the highest level of generality because I just need to see as an econometrician the choices you face, nothing else. It's of course a very complex experiment as well because I need to have a lot of choices variation. So for the cars example, this is just an abstraction because I will need to see markets in Canada where all possible elements of this power set of the set of cars is possible, right? So for instance, London is going to have 3 alternatives and Thomas 2. And then, you know, we have another Hamilton when you have another permutation of these elements, such as I have variation in the choices. Usually that's hard to have, and you only have partial variation. So I'm thinking now of an experiment. So this is just an experiment. So it's hard to get in real life, but it's easy to get in an experiment. And this is just because we want to understand in this ideal setup the empirical part of logic, right, without the noise of real data. So now the loose IIAs, the independence of relevant alternatives, means that for any 2 menus in this collection of menus, and any 2 alternatives that live in the intersection of the menus, I have this equality of ratios, right? So the probability of A divided by the probability of B conditional on the menu A is equal to the probability of A divided by the probability of B conditional on the menu capital B, whenever the probabilities are positive. So this is only defined for positive probabilities. And then there's this famous theorem by Luce and McFadden. So the following are equivalent if the probabilities are positive. So this stochastic choice rule satisfies IIA, and the stochastic choice rule admits a logit representation. So right now I'm going to take a break of 5 minutes, and then I'm going to continue with the proof.